Good morning. Today is March 17th, 2018, St. Patrick's Day. And this is the John Chappell Natural Philosophy Society Science Chat. I am your host, Franklin Hu, and this is sponsored by the CNPS. Please visit our website, naturalphilosophy.org. You can join us. You can join our forums, and you can find us on Facebook. And we do have a conference coming up on June 27th to the 30th at the University of Connecticut. So please join us there if you can. So today is an open forum, and I believe we have a question from Harry Ricker. So Harry, go ahead and state your question.
All right. Well, as everybody's probably heard by now, unless you've been in a time warp, that Stephen Hawking died. I guess it was on the 14th of March. And everybody, in the forums, everybody, was really quick to, oh, Stephen Hawking died. Oh, he was the smartest man alive. And there was a lot of chit chat and talk going on. And everybody was talking about how brilliant he was. He was the smartest man alive. But I couldn't find where anybody ever said what it was he did to justify being called the smartest man alive. And even the BBC had a blurb about Stephen Hawking. Of course, he was British, so they had to, make him out as a hero. And the moderator, who was this woman, said, oh, he was the smartest man alive, but she admitted she knew absolutely nothing about physics. But it was obvious that he had to have been the smartest man alive, and he was a brilliant genius and had contributed so much to our knowledge of physics, although she didn't know anything about physics. So my question is, what did Stephen Hawking do to justify being considered the smartest man alive? I'm sorry, I can't figure it out. Anybody have any thoughts on this?
So what do people think? Was Stephen the smartest man alive or not?
Well, that's not really the question. I'm just not sure what he did. What did he do? What did he do physics research in?
Well, a lot of
What
it
did he
was
discover? Does anybody know?
Yeah, a lot of it was cosmology. He's especially famous for the science of black holes. And he, one of his most famous things that he said was that they emit what is called a Hawking radiation, which actually causes black holes to evaporate. So I would say that
that's controversial. I mean, that's not. I mean, that's one of the more obvious and more talked about claims that he made, but that's kind of not really agreed to, or that's controversial. I mean, a lot of people claim it's not true. It's still kind of an issue of where they're still arguing about it. I wrote a piece on that, by the way. I couldn't really make any sense as to whether or not they'd actually established it was so or not so. So that doesn't really count, in my opinion.
No.
And as far as cosmology is concerned, I don't know that he made any significant contributions to cosmology. Pretty much cosmology had been fairly well established. The Big Bang Theory was pretty well established before he did anything. And I don't know that he had anything with the modern theory of inflation, which is considered the modern view of cosmology. So I don't know if he had anything to do with that. So I don't know that he had anything to do with anything in cosmology that is considered significant or important. So does anybody can tell me what it was that he did?
Well, I'm trying to share a screen, so this is entitled, "These are discoveries that made Stephen Hawking's famous," or whatnot here. So let's see what they say. Let's see here. He didn't discover black holes or the Big Bang, as you have mentioned. So what did he do, according to this? Can you see the screen? I'm just reading it myself here. Several polls, Hawking is either absent or crawls on the bottom of the list. So actually on the list of greatest physicists, Hawking doesn't really make it on the list, which is interesting. So for someone
apparently he didn't get a Nobel Prize, so he's not even a Nobel Prize winner.
No, he's not even a Nobel Prize winner. So that's interesting. That's how this whole article starts out. He didn't get a, and he's not Albert Einstein or Isaac or Newton. So let's see here. What?
If I remember right, I think his popularity really took off after he wrote that book. That book about time or something. That's, I think, when the general public really started taking notice of him, I think.
Well, it looks to me like he's just a garden variety minor physicist who they just sort of decided to turn into the smartest man alive through publicity. So that ought to make us beware of the fact that physics really isn't about substance as much as it's about publicity.
Yeah, and I think David DeHilster talks a little bit. I just posted a link on the chat. He just posted a video on this whole idea, and he kind of goes into this subject a little bit too, and raises the fact that he also believes this, that a lot of it is because Americans, and just Americans, a lot of people around the world, they do have the fascination of somebody that overcomes a lot of obstacles in their life and makes a big impact in certain areas. I'm not saying that we do have to admit he did make a big impact. Whether his theories are true or not is a different subject, but he did have a big impact, and there's no doubt that he did overcome a lot of personal setbacks and in his life because of his disability.
Did you see the movie?
No, I didn't see his movie.
I forget the name of the movie. Do you remember the name? Anybody remember the name of the movie? I forget what the name of the movie was. Genius or something? I don't know. I know I saw that movie and I was really kind of stunned when I saw the movie because essentially his wife pretty much did all the work and that allowed him to do his papers and everything. And then after he became famous, he divorced her, which I thought was kind of, I thought he came off looking kind of like a jerk. So I don't really understand how when they make a movie about a guy who is supposed to be flattering and he comes off looking like a jerk, why do people consider him such a hero?
Yeah,
there's the movie, The Theory of Everything, on the screen.
Yep, there it is, which seemed more like
quite frankly, I thought he came across as a class 1 jerk in that movie. I don't think the movie was actually flattering at all.
Well, that seems the way.
Did you see the movie, Bill?
I saw the movie, yes.
What
Also,
are your thoughts?
The book he wrote was A Brief History of Time.
I have a copy of it, yes. And it's just kind of like, it's not that interesting. It's just kind of like, you go through you recite it's a summary of what's in cosmology textbook, basically.
I think what caught people's attention was how he overcame such huge physical problems with his health and was able to make a contribution of some sort to science. In other words, he represented a person who was an overcomer, and that they liked.
But as the movie showed, that was really due to the fact that his wife worked her ass off. So I don't understand why she didn't get the credit.
Yeah, it seems like Stephen Hawking is like one of these quote unquote rock star scientists. We have, you could say like build a science guy, who hasn't contributed anything, I don't think, is unarguably one of the most famous science personalities on the planet, right?
And yet we can't figure out what it was that he did. I can't pin down anything that I would say that I don't know of any contributions of any significance to cosmology. Certainly nothing.
Is that a matter that you don't believe them? Because obviously the thing that he contributed was the stuff about black holes. So I think that stuff did genuinely belong to him.
Black holes isn't really cosmology, but
it isn't. No, whatever you call it, was his contribution, I guess. Of course, I have a doubt whether black holes really exist the way that they describe them. But
what has happened with black holes is that they have sort of whatever it is that they looked out and they found. It's pretty well established now that they believe that black holes exist, but the reasoning is sort of on the order of, well, there are these things that they see in the centers of galaxies and in other places that they really can't explain. So they've sort of grafted the idea that they're black holes. But black holes are supposed to suck everything into them, but these objects that they observe are doing the opposite. They're pushing stuff out. And so then they've evolved this rather complicated theory of accretion disks and this other, it's kind of hard to really make sense out of. But so essentially what they've done is they've said that because black holes have to exist in theory, according to them, they've just identified the mysterious things that they found that really can't be explained by anything else are black holes. Does that kind of make sense to you, what I just said?
Not exactly.
You don't understand that you have a theory about an object that exists in theory, and then you just sort of take something that you observe out in the centers of galaxies that you don't understand, you can't explain, so you call it a black hole.
Yeah, I guess I can kind of understand that. But I guess my question is that the characteristics of a black hole is supposed to be that thing that's supposed to like suck in light.
A black hole, basically, essentially what it boils down to is this. A black hole is any object that exceeds the mass, a certain mass limit, okay? And so any object that has a mass that exceeds that limit, okay, has to be what they call a collapsed object, because their theory of gravitation says that if you have more mass than a certain amount of mass, it has to be a black hole. So they look at the centers of galaxies and they say, oh, the velocity of stars orbiting around the centers of galaxies are moving pretty fast. So when we calculate how much mass has to be at the center of the galaxy, it turns out to be billions and billions of solar masses. And so that just can't be there because the theory of gravitation says that anything that small can't really exist as a normal star, so it has to be a black hole. Does that make sense to you?
Well, my question is that what evidence do we have that there is such an object which has the minimum radius, I think it's called a Schwarzschild radius. Why couldn't these things that we're observing just be very, very large lumps of rocks?
Because the theory of gravity says they can't exist as lumps of rocks.
I don't think the theory of gravity would say that. I mean, it's kind of, you'd have to know what the limit that ordinary matter can be compressed, I suppose, to say that.
Well, because
law.
their theory of gravity says that if you exceed 1.4 solar masses, okay, then a star can no longer maintain its thermonuclear reactions and generate enough heat energy to prevent the collapse. It must collapse to a black hole, because that's what the theory says.
Yeah, and that's the problem. It's a theory, which is made out of math, which
Well, the
might
theory's not
work,
wrong
or
because they've confirmed it every place other than in black holes. So since they've confirmed it according to them, they've confirmed it with respect to the orbit of Mercury and these other instances. They prove that the theory of relativity is, quote, correct. And so therefore, since the theory is correct, and since it's predicting that black holes must exist, then therefore they have to exist because the theory says so.
well, I would say the theories say that black holes can exist. That there's a lot of ifs here. That if you take, something that's 1.5 solar masses, and if you compress it down to something, I don't know, the size of the Earth or whatnot, or whatever it is, that it will have X amount of gravitational force around it. So that's a lot of ifs. So I don't know that predicts that that's possible.
Well,
But
it's
then
a
again,
lot
I
easier
don't.
to get a published paper saying that you've discovered a black hole when you found something that you didn't really, that wasn't predicted. And so you find these, essentially this started in the 1960s. And the main thing that they discovered was that these active nuclei of galaxies, and you have a whole bunch of them. There's Seyfert galaxies, but the real idea was that quasars were galactic centers. They were the centers of formations of galaxies. Then some people even speculated that the galaxy was invisible because the quasar inside of it was so bright. And they couldn't really understand what a quasar was because it was putting out more energy than what was, it was an impossible amount of energy. It was so tremendously bright. And then when they started connecting these quasars to the centers of galaxies and finding similar radiation and emission patterns inside the centers of galaxies, then they sort of came up with this idea of supermassive objects. They were called supermassive objects. There were a lot of different theories about this. But over the years, they've sort of gravitated to the conclusion that these objects are supermassive black holes at the centers of galaxies.
Now I'm looking at the wiki entry for black hole. So I've highlighted what appears to be Hawking's primary contribution. Looks like this guy has, made his whole career off of this. What's in this one paragraph? He's kind of like a one-trick pony, isn't he?
Well, okay. I guess we've decided that we don't know what Hawking did.
No, this is what Hawking did. I don't know why you don't think that this is what Hawking did. I mean, this is what he did. He did this whole Hawking radiation thing. He's got something named after him.
Yeah, but so
clearly he did something.
That's kind of controversial. I mean, it's
it is.
Really...
I mean, it doesn't matter that it's controversial. That's what he's known for. When people ask, that's what he's known for.
I mean, lots of people have done things like this. That doesn't make them. That doesn't justify calling them the smartest men in the world and justify all these eulogies and television and on the internet and everybody just swooning what a brilliant guy he was, because of all of his contributions to science. So I'm just kind of to me it's kind of puzzling.
Well, I don't know. For me, it looks like he made one contribution. If you've got something named after you that people know about, generally, I guess that's pretty good.
People have those things. They don't necessarily consider the smartest guy in the world.
Well, usually when you get something named after you, like Volts and stuff like that, and Curies, usually those people are considered at least very famous. We need to, like, if you had Ricker radiation and everybody you talked to knew about Ricker radiation, then, well, that would certainly be a feather in your hat, right?
Well, it might be if it was something that, wasn't considered, I mean, it's kind
Well, I mean,
of,
actually, Hawking radiation is pretty well accepted in the mainstream. Here in the dissonant community, we
yeah,
don't believe anything, but
maybe, I don't know. I mean, it's still not considered, you know, for something that's a theory about something that doesn't even really, we don't even really know is convincingly exists like black holes. I mean, it seems sort of peculiar. I mean, black holes, that's sort of, even that's sort of suspect in my mind. We just talked about that.
yeah, it's kind of so it could be he invented something that's based on something that may not even exist. So,
Well, I think we know that it was Hawking radiation that is the most well-known of his so-called, quote, discoveries, but it still doesn't explain why he was considered the smartest man alive. And because of his work in theoretical physicists and physics, and then we go and we look, and the people say, well, he made these important contributions to cosmology, and I certainly don't know of any of them.
It would be interesting to find out that if Stephen Hawking did not have his disabilities, if he would be as famous as he was, or if I guess if people would even know about him as much.
so here's the question: is Stephen Hawking the smartest man alive? See, I love the internet because if you got a question, someone's asked and there's an answer. Okay, so 49% say yes and 51% say no.
It's pretty narrow margin. I would have thought it would have been like 10% yes and 90% no.
No, it's a coin toss here.
Well, what this tells me is that people say if people on TV and in movies and on television say that he's the smartest man alive, then a lot of people will believe it, apparently, according to what this statistic says.
So, we have these remarkable achievements in the field of relativity and quantum physics. So once again, that would be the black hole thing.
What were the remarkable achievements?
Well, like I said, the only achievement that we can really think of is this Hawking radiation thing. And that covers relativity and quantum physics. So there's that one thing.
This guy named Ellis, which I can't remember the guy. His name was Ellis, and I'm not really sure whether Ellis wasn't his the lead author of the book. So that a lot of people were taught black holes and cosmology using that book. And so I can understand why a lot of scientists would say, oh, yeah, he's a real smart guy. But the question is, writing a textbook with another collaborator, I don't know that makes you the smartest guy in the world. Lots of people have written textbooks on relativity and cosmology and are not considered the smartest man in the world.
Yeah, see, all these yes comments are referring to his Hawking radiation. So I don't know if that if that makes you smart. Yeah, everything. It's kind of interesting that he doesn't seem to be like a one-trick pony. He parlay an entire career off of one thing you've thought about. But a lot of people are referring to, they as Bill mentioned, is that he overcame a great disease and he's kind of famous for that. He's a rock star scientist. He may be more like a science ambassador because when people write these books, A Brief History of Time, I mean generally they are just a very large explanation of cosmology in general, and generally sticks with the mainstream, and they do that and it's written in a way that lay people can understand it, and because that's what sells. So he's definitely famous.
This may be an example of one of the examples that I have was my father worked at NASA at NASA for years and years. And he never liked Carl Sagan, who he said that he'd been to a number of meetings with where Carl Sagan made these presentations. And he kind of thought Carl Sagan was a bit of an ass. And, so every time, people would talk about what a great, brilliant guy Carl Sagan was, my father would get really irritated because, he actually knew the guy and worked with the guy and didn't think there was anything brilliant or impressive or smart about the guy. And so I think this is just another example of it's all about publicity and not really so much about accomplishment.
Yeah, that may very well be true. It's a popularity contest, right? Who's most popular?
Okay, I guess we've ascertained that we haven't identified anything that we can really say that other than Hawking radiation, which is controversial.
Yep, I would say that's probably where we're getting to there. But at least you got one thing. Hawking radiation. Okay, that's the one thing he did. Big deal for something that may or may not actually exist. But if they do exist, then yes, black holes will eventually disappear, so we don't have to worry about them.
In 2009, Stephen Hawking received the highest civilian honor in the United States, which is the Presidential Medal of Freedom. So, he has received some awards, but we don't know exactly all the things that contributed to that. But his main books are The Large-Scale Structure of Space-Time, Black Holes and Baby Universe, and other essays in another book. And then another book was A Brief History of Time. And then another book was The Universe in a Nutshell. And so he did a lot of publishing and that sort of thing. He was he held the post at I don't know if it's Oxford or Cambridge, one of those places, the Lucasian Professor of Mathematics, and that was the position held by Isaac Newton when he was teaching in the university. So
he wasn't actually a professor of physics.
He was in mathematics, yeah.
He was a professor of mathematics.
Yeah, so there's another irony for you there. The guy's considered to be a brilliant physicist, and he was a professor of mathematics. He probably never did a physics experiment. And
but remember, Isaac Newton held the same position, and we consider him a great physicist.
I know. That's kind of ironic, isn't it?
Yes.
Well, physics has been basically taken over by mathematics, so I don't particularly find that surprising. People like Newton just took what they observed physically and was able to describe them mathematically. And largely everything
I was saying before, Franklin, which is that because the mathematics tells you that black holes must exist, according to the mathematicians, people that are really mathematicians who dabble in physics are called theoretical physicists. That's kind of an ironic designation. They don't really do physics, they do mathematics that is supposed to be applicable to physics. Okay, so that's a theoretical physicist. So according to theoretical physicists who do mathematics, black holes must exist because they say so, because their theory of general relativity says that they exist. Okay, and so then you have the people who do the real world astronomy. Okay, and they go out and they find some object that's emitting more energy than it's supposed to, and they scratch their heads and they say, what could this possibly be? And they look over at the theoretical mathematics and they say, black hole. Oh, this must be a black hole because this, we can't explain it with our regular concepts of what a star is, so it must be a black hole. That's how they're doing things.
So how would you compare Stephen Hawking's and Marilyn Savant.
What was that?
Marilyn Savant.
Oh, I
She's
know who you're talking about. Yes.
most famous also, famous and smartest person alive. So we can
She's
have,
famous. Yeah, I know who you're talking about. Do you know who he's talking about, Franklin?
No, I don't. Who is this person?
Marilyn Savant, who had one of the highest recorded IQ ratings. She took an IQ test and got, it was like 176 or something. It's off the chart IQ. And she writes this column for Parade magazine.
and answers questions too.
Ask Marilyn. And there's a controversy that she got into about, and I read about this a couple of months ago, about probability calculations. And she got into a contest with some mathematicians about probability calculations, where she answered one of the questions in her article, and that resulted in kind of a big brouhaha with the mathematicians. And I think she generally came out okay in that argument. Do you know what I'm talking about?
Who are you asking the question of?
I don't know whether Powell knows about this or not.
I don't know the detail, but I've heard both in same context as the smartest person alive.
Yeah. Well, in her case, I think it's more of a showbiz kind of thing. In other words, she is entitled to that because she's like a show business personality. Okay. And so that's she's not really pretending to be a scientist or anybody. That's just like, you introduce a showbiz personality as being, such and such, such and such. So she's introduced as the smartest person, and that's kind of like her like showbiz gig, so to speak. But I don't know that she really has done anything to deserve having that said about her, other than she claims it as a title.
I mean, ultimately, that would, I don't know, that has to be some kind of a judgment to say that someone's the smartest
Same thing about Stephen
anything.
Hawking, just because people it's a sobriquet. You know what a sobriquet is? I don't know. I'm pronouncing it correctly. It's a French word. It's like, a phrase that gets attached to a person, and they it becomes like I'm trying to think of some examples, but I can't. Do you know what I'm talking about? Where, this person is dubbed a hero because he did something heroic. And I guess the guy that landed the jet plane in the Hudson River, I guess, don't they have a name for him? They made a movie out of that. And, and he's the hero of the Hudson. Isn't that what it is? And so that's called a sobriquet. I don't know that I'm pronouncing it correctly. And it's just, a phrase that attaches to him as a person because of something that he did that may or may not have been all of that amazing or deserving, but he gets that attention anyway. So I think maybe this is what we're dealing with Stephen Hawking.
I was wondering, Henry, do you have a particular reference we can look up on the internet where someone is saying that he's like the smartest man alive? Was there like a BBC interview?
It was just on here.
Well, there's some questions there, but I don't know that I've seen a particular quote saying that. I just wondered whether something that was particularly
got
your eye.
That's one of those things that, like a journalist might want to research. How did this sobriquet get attached to Stephen Hawking? And, you would sort of wonder, well, I'm asking myself when I see people saying this, people were saying this, And I'm asking myself, well, what did Stephen Hawking do to get this, title, the smartest man alive? What did he do to get this title? And, and I'm asking the question, I can't think of an answer. That's why we're having this discussion. But anyway.
Seems like a People magazine thing, right? They always pick the most beautiful guy or girl in the world, and they stick them on the cover, right?
Okay. Well, I think we
Someone has
spent
to
too much
decide.
time on this. I was hoping that somebody out there who was participating would have more information, but that would be able to defend this, and apparently not.
A lot of articles I read that do claim, that do have lists of people that are the so-called smartest people on Earth. They give their IQs to kind of back up that claim, which to me has a little bit of credence behind it, because at least they have something to back it up there. Do we know what Stephen Hawking's IQ is, or has anything like that been published?
I don't know. I think it'd be in the wiki if it existed. IQ. Let's see here.
I think it all basically is PR. And
probably just take an IQ test.
To me, it's kind of, I don't know. Okay, we can move on to another subject.
Yeah, well, actually, if you look at the most recent issue of Popular Science, there's actually a whole article on the science of figuring out who the smartest is, which includes things like IQ tests and tests that were given by companies like, IBM or whatnot to separate out their candidates, and what tests that NASA used to qualify people for space flight and stuff like that. I think it's all a bunch of hooey. But you could be the smartest person on Earth. Bill could be the smartest person on Earth. But there's no, everyone has different abilities and may be the smartest person on Earth on different things.
Well, I think my point would be, this is kind of what my point is about this. And that is, I think that physics theories are sort of like physics personalities. Why do we say that a certain physics theory is true or not true? Why has everybody sort of decided that Einstein's relativity is the correct theory? And there's all kinds of theories out there, where I think this applies. Is it all about PR and publicity that a physics theory becomes the accepted theory and everybody sort of gloms onto it and promotes it and says, yeah, I believe that theory? Is it because, it's really a true theory, or is it because by some accident of society and the way people think, it's just become the popular theory by some kind of accident of human behavior, like this guy, Stephen Hawking, has become the smartest man alive, and we can't really figure out why?
Well, I would hope that the scientific method at least helps support what are these most popular theories. So if relativity is popular, that there are experiments to at least back what they're saying theoretically. But that would be one area very.
That's kind of really the issue. I mean, is a theory about Hawking radiation, is that accepted because there's any real evidence for it, or is it accepted because the smartest man alive invented the theory?
Well, that's a good question. I would kind of say, since we haven't actually seen a black hole and sent a satellite around to study it, or pointed a telescope capable of resolving whether this happens, then it's like, oh yeah, well, maybe it's famous because it's interesting, and it can't be either proven or disproven, and this guy wrote a lot of books and he's famous, so maybe that's why it's accepted.
I think that's, you kind of hit the nail on the head when you said it can't be proven or disproven. I think that's a big part of it. So you got to pick one of them, I guess. So I guess these end up getting picked because they're written by people that are popular and who seem to know what they're talking about.
Yeah, and there's just like piles and piles of math that that only the high priests of quantum physics can really understand anyway. So the rest of us mortal beings have no chance of ever understanding exactly how we justify this stuff.
The theory of black holes has been somewhat disproved by a person who worked at NASA, Ed Dowdy, and what he showed is that black holes, according to special general relativity theory, should bend starlight, and we take the black holes that we have identified and you watch their motion in the constellations, and we see that the light is not bent like it's supposed to. And so we have all these different contradictions that are occurring, and instead of falsifying the theory of black holes, they invent something to get rid of the problem. Just like when the failure of general relativity, when spiral galaxies, they invented dark matter and dark energy, and you can say, well, it's a fudge factor, but the fudge factor there's 24 times as much dark matter and dark energy as there is regular matter and regular energy, and so that's a very big fudge factor. Some people think that this is all kind of nonsense in some sense.
Well, there have been, I've just watched, there was a special, How the Universe Works with Morgan Freeman. Now, there was a whole episode on black holes. And, I thought they gave it a fairly good treatment. I mean, the premise was, do these things actually exist? And, they presented, it wasn't just a slam dunk for, yeah, they exist. And so there was certainly, even in the mainstream, you can see the controversy around black holes. So like I said, my question is
on observational facts. That's the problem. So what you have is science supposed to be based on observational evidence? Now, to a certain extent, I can understand cosmology in that, let's take cosmology as an example, okay, if you will. What are the facts that cosmology is based upon? Can you tell me what the facts are that cosmology is based upon, the actual experimental evidence?
Other than we look up in the sky and we see stars?
The primary experimental evidence is that when they measure the spectral lines of galaxies, the spectral lines of galaxies are shifted to the red relative to the same spectral lines as measured on the Earth, and that according to their measurements of distance, which are, crude to say the least, there is a redshift distance relation which says that as the distance or the supposed distance or whatever they think is the distance, they distance measure whatever they have a yardstick of distance for, that as that distance measure increases, the redshift measure increases. That's the experimental fact upon which cosmology is based.
But there's contradictions to that, because at Princeton University they measured the gravitational redshift, and so if you're looking out and at a distance from the Earth, which are you seeing, a Doppler redshift or a gravitational redshift? And if the force of gravity was stronger in the past, the gravity can explain all the primary amounts of redshift, and so that's been a problem we have. We have so many contradictory explanations for various things, and the people who look at the Earth more closely say, oh, the Earth has expanded something like 70% in radius in its history, and that means that the force of gravity was stronger in the past and it's weaker now. And when we try to measure gravity, we can't measure gravity to 3 significant figures and get a consistent value over time. Gravity is changing, and gravity at different points of the earth is changing. And so it's not like atoms and stuff like that where you can measure the whatever you're measuring to 8 significant figures. We can measure to 8 significant figures, but they only agree to between 2 and 3 significant figures. And so there's something going on there, which scientists don't want to admit that gravity is decaying. And the data that shows that gravity is decaying is not allowed in most journals and not allowed in college or university courses or high school courses because of the education framework, which is designed to support the politically correct theories, not the ones that are scientifically correct or logically correct. And so I've been studying, for instance, the rate of rotation or spin of the Earth. And when you look at the coral reefs, you'll find that they have rings, just like tree rings. But unlike a tree ring, the coral rings have a ripple in it, and the ripple corresponds to each day of sunlight. And what you find is the rings that are made recently have approximately 365 ripples. But in the past, they had over 400 ripples, which indicates that the Earth was rotating faster in the past. And so we know from ballerinas and people like that, that if you're rotating fairly fast and you put your arms and your legs out, you slow down. And so as the Earth expands due to decay of gravity, the rate of rotation slows down. And we have also the stretch marks on the bottom of the ocean showing a 3-dimensional expansion of approximately 70%. And so all of that indicates that we're not treating gravity correctly, but they don't allow any of that data in the textbooks because it's
I don't think we're treating gravity correctly either. Although, so far as the expanding Earth theory goes, my feeling is that the amount of matter is actually being produced in the Earth, which is causing the expansion rather than, say, a reduction of gravity. I mean, both things are possible. Although I would think that if you took the Earth and you just turned off the force of gravity, I don't think that it would just immediately become, I don't know, fluffier. I think that that's mostly determined by the interatomic bonding. So I don't feel that even if gravity was decreasing in strength, that would cause an expansion of the Earth. It's just like if I had a block of steel that was like 1 cubic yard in dimensions, and I take that and I stick it out into space where there's no gravity, I feel that it would not expand at all. It would stay exactly 1 meter cube, whether it's under gravitational influence or not. But that's just kind of my feeling. So, but I would have to explain.
Well, the GPS shows it's expanding every year. That we've had the GPS, we see the Earth is three-dimensional expansion.
I'm not saying that doesn't happen. I'm just saying what is the cause of that expansion.
Mass is not created in the Earth. The Earth, as far as we can tell, when we look at the motion of the Earth with respect to the Moon and stuff like that, we feel that the data does not support that we're getting more mass in the Earth. It's just getting larger. It's kind of like a balloon. When you put hydrogen in it and it goes up in the atmosphere, there's the surface of the balloon is holding it in, but as you go up and it doesn't get support from the air of the atmosphere, the balloon expands until finally it blows up or cracks.
I mean, basically you're talking about decrease in density is what's causing the expansion. So although you really can't tell what the mass of the Earth is by orbital mechanics, because that basically the mass of the Earth basically cancels out. So it's whether you're a ping
All
pong
you need is a
ball,
pendulum. A pendulum can let you measure the mass of the Earth.
well, whether you're a ping pong ball or the planet Earth, they're all going to orbit at the same rate in the same orbit. The mass really doesn't make any difference in the orbit. So I'm not quite sure how you can say that we've not been able to determine whether it's a decrease in density or an increase in mass.
But see, the increase of mass you measure with the force of gravity. So if the mass is increasing, gravity would be increasing, but gravity is decreasing. The surface of the Earth, gravity is decreasing. That's why we can only measure it to between 2 and 3 significant figures for big G. Because
well, I don't know that means that it's decreasing. It just means we have a hard time measuring it. It could be increasing, could be decreasing under.
We can measure it to 8 significant figures, but if you take 2 measurements the same day in the laboratory, you'll get 2 different answers.
Yeah, and that's fine, but that's not neither support for increasing or decreasing gravity.
If you do an atom, you get the same result day after day.
Yeah, but I'm just saying that is neither evidence for an increasing or decreasing gravity. It just means that gravity varies.
Oh,
that's
it
evidence
does.
for
It's
varying
going
gravity.
down. The force of gravity is going down, decreasing.
You'd have to show me.
You go back to the time of Isaac Newton, they measured a stronger force of gravity than we measure today.
Well, I haven't heard about that.
Yeah.
Well, actually, Franklin, this has been talked about quite a lot. But as Bill says, that's not really one of the assumptions that they want to use, because it kind of complicates everything. If you assume, if you're doing mathematics, okay, and you kind of assume that the G is a scalar quantity that's unchanging, it makes your mathematics a lot easier to work with. So, then when you start doing like Bill is saying, as you talk about changing of the gravitational constant, then that faces a lot of issues, like people like what you just did can basically argue they don't believe it. And so then you wind up with, sort of a stalemate. And the people who are producing their mathematical theories on the assumption that G is a fixed constant can continue to go on and do that. And to a certain extent, that's what they've done. So they're happy doing that because it makes their mathematics work. And they don't want to have to go back and redo all the mathematics and all of the, paper publishing that got them to the point where they're at now. So, but the point I was making earlier was that the real primary observation of cosmology is the distance redshift relation. Then later in the 1960s, they discovered the cosmic microwave background radiation. So you have 2 facts, okay? Now, given all of the possible theories that you can construct, given 2 facts of observation, seems to me like you've got a lot of theories that you can fit into 2 facts of observation. So why would you say, I don't really understand it. How can you say and appear on TV and say that the Big Bang happened and construct all these wonderful theories of the universe based on such a small observational set? To me, it's just preposterous.
I'd agree. That's preposterous. The whole Big Bang theory just seems kind of ad hoc, really. So.
Yeah, but it fits the mathematical theories that they can construct given the general theory of relativity. So you have the general theory of relativity. Basically, cosmology is exceedingly dumb and simple. It's nothing more than a differential equation, first order differential equation that says, you can have the solutions. You can have the solution of an exponential expansion. You can have an oscillating solution, or you can have a collapsing solution. And then you've got all these parameters that you can plug into the solutions. But the mathematics, despite the fact that it looks really complicated, really basically is nothing more than a simple differential equation. If you make the universe more complicated, if you have a theory that's more complicated and you can't use that simple differential equation anymore, then you can't say that you have a theory of the universe. So it's a lot easier just to stick with that simple theory that they have and sort of change the parameters of the theory, because they can do that and they can sort of convince themselves that it's true. But it's still based on very slim observational evidence.
Well, there is actually a lot in cosmology. I was reminded that, one of the reasons why they think, say, the Big Bang occurred are these nucleosynthesis arguments, which is that they can, based on their theory, predict what the distribution of the elements should be. And that's based on our Earth-based physics experiments and nuclear reactors.
That theory ran into a problem because they could only produce the element helium in the Big Bang and no other heavier elements. And so that theory kind of fell flat on its face. So that's another example of if you use the basic theory, simple differential equations, the Big Bang theory, the problem is you can only synthesize the elements hydrogen and helium, and that's pretty much it. So where did the rest of the elements come from?
That would be the other area, cosmology, which is how they think the sun operates. So there's a lot of cosmology around that.
Then a smart guy comes along and he says, oh, well, we can produce the other elements by nucleosynthesis inside the stars. Okay, so yeah, right. Hey, great idea. So this is an ad hoc hypothesis now. There's no observational evidence to justify it. It's just a theoretical guess. And so now they were able to say, oh, yeah, we can manufacture carbon and nitrogen and all these other elements, but they get to a point where they can't manufacture anymore in stars. Okay, and I forget exactly how far they go up the chain, but they don't go anywhere that far up the chain. Okay, and now they're stuck. Oh, and then some other guy came along and said, oh, we can explain it by nucleosynthesis in supernova. Yay, we solved the problem. Okay, it's just a chain of ad hoc assumptions, but no observational evidence to justify any of that.
Well, that's certainly possible. We've been able to transmute elements here on the Earth in the atomic reactor, so we kind of know it's possible.
Having something possible doesn't make it into a true theory. So what you need is some observational evidence that justifies what you're saying. They don't have any observational evidence. They only have two facts, basically, and the rest of it is a lot of ad hoc theoretical kludging in. They don't know that there are any fusion reactions going on in stars. They don't know that heavy elements are produced in supernova, because we don't have any supernova around that we can produce in a laboratory that we can make measurements of. It's all just theoretical, making mathematical theories that make it look like it's plausible. That's not science, in my opinion.
Let's see, looking up then at this question. So here's, I just brought up a chart of the abundance of elements in the solar system. So what I see most interesting is this zigzag pattern that every other element is more abundant. So that's kind of curious. Why is it that every other element is more abundant? And then we see some unusual spikes in here, like iron is a very unusual high amount, and scandium, I guess, is unusually low. Lead seems unusually high. Beryllium looks really unusually low, along with fluorine. So I think those are probably the real clues to what makes atoms in the galaxy. There should be some reason for that.
And lithium is very low, you might remark as well.
Yeah, lithium and boron seem really, really low relative to where you would think they would be.
Well, this is not measured. This is predicted by the Big Bang Theory.
I don't think so. I would hope this is empirical. Let's see, what do they say about
in
this?
the first sentence underneath there.
I don't think that the Big Bang would predict this zigzag effect at all.
I don't know.
And I know iron is unusually abundant in the solar system as empirically measured. I mean, there's no reason why iron should be that present. I mean, I work with alchemists, and they explain things like the reason why iron is so abundant, because it's kind of, if you look in the energy curve, you know, it's right in the middle of between fission and fusion. So basically, everything that can try to get to iron will get to iron. So things like carbon and oxygen, you get enough of those atoms together. One of the main things that will come out, just because it's energetically favorable, is iron. So they explain.
You would expect iron to be at the maximum.
Well, it seems to be at a local maximum. It's certainly not more abundant than carbon and oxygen, but it seems to be unusually present in the observed elements. So, I mean, the rest of the curve you can kind of explain that the heavier elements are just rarer. So there's just a steady curve downward there. But we've got like this unusually low scandium, unusually low beryllium, unusually high iron. If you look at beryllium, you know, why should that be so low? Now, beryllium would basically be gluing two helium nucleuses together. And I don't know, maybe that's why beryllium is so low, because if you ever made beryllium, it would just break up into two helium nucleuses. You know, that could be a potential reason why they're so low, although that doesn't really explain why lithium and boron are so low, but you can speculate. But, you know, this is an interesting piece of data to look at, which is abundance.
I don't know that it really tells you anything. It's not, in my view, kind of definitive. You don't know
it's just data.
They calculated it, what corrections they put into it, you know, what assumptions they made in doing all these different measurements. You know, it's really kind of, you know, hard to really get a handle on it, which makes it difficult to understand. But you know, the bottom line is, okay, now if we look at astronomy pictures, which is my hobby, don't you think we ought to be seeing things out there that kind of conform to their theory? No, we don't. What we see is in nuclei of galaxies, we see a lot of stuff coming out. We don't see a lot of stuff going into the black hole. Why is it there's all this stuff coming out? Okay. And stellar, so-called star-forming regions, it doesn't look like the gas and clouds are collapsing to stars. It looks like the gas and clouds are coming out of the stars as they're being formed. So gas doesn't condense to form stars. The gas comes from the stars when they form, okay, and are created. So everything that we see observationally is the opposite of what the theory tells us ought to be so. But because people look at things through their glasses of theoretical interpretation, they think they see something that's happening that's not happening at all.
So do we have a better explanation?
Well, that's one of the problems right there. Okay, you say, do we have a better explanation? It's not a question of having a better explanation. It's having an explanation that is consistent with the observations. Okay, you've only got two observations in cosmology, as I explained, and they built a whole theory of the universe based on two observations, and all the rest of the observations are kind of like not really paid any attention to at all.
Well, the real kicker in all of this in modern science is that we took the role of logic out of modern science. So it's not possible with this current scientific method to discover truth. And I'll give you an example of that. Relativity theory assumes the universe is homogeneous and isotropic. That means it's the same in every direction. And it has no center. But
Yes.
we find our solar system has a center. Our Milky Way galaxy has a center. Every galaxy we see has a center. And if you use proper logic, you find that the universe has a center and all the galaxies are in shells about that center that have the same quantization as our solar system, called Bode's law. And but we don't use logic. And logic says if there's any assumption in your theory that is known to be false, like the universe is homogeneous and isotropic, that theory is falsified. Don't do that.
That's an interesting point there, Bill. The point of it that is that the assumption that you just stated, uniform and isotropic, I forget exactly the way they say it. They call it the cosmological assumption, or that's that the universe is uniform, isotropic. That makes the mathematical equations that lead to the differential equation that I was talking about. You get a series of differential equations. It makes it possible for you to get to those equations because you simplified out all of the complexity. And so by making the simplified assumption, then you get this simple differential equation. Actually, it's not an equation, it's a set of equations. And they try to pick the one out of the set, an infinite set of equations. They try to pick the one out of that set that agrees with what they observe in terms of redshift and distance relations. Okay, so if you don't have that assumption in there, then you don't have cosmology anymore. The theory falls to pieces. So they need that assumption, right, Bill?
Well, it simplifies, but there's more to it. I'm writing a series of papers, 10 papers showing that the 10 most significant theories in modern science, which obey the modern scientific method, which took the role of logic out, but had been there for thousands of years. If you look at them, they have one thing in common, all these theories, and that is they were each designed to nullify or falsify something in the Bible. And that was occurring, these theories were all developed at the time that the Second Great Awakening occurred in America. And so what you see is there's goals that people have in science that causes them to make the simplification so they can get the theory that they like. And Francis Bacon in 1500s, the way he expressed this was, man prefers to believe what he prefers to be true. And that's what modern science is doing today. The theories we have are what the leaders prefer to be true, and if they want the conclusions of science to support their preferences and their beliefs and what they would like. So when the Second Great Awakening occurred, people were upset because people were being convicted of sin and of the power of God to take care of that, and morality, and they didn't want that. And so they said, well, we're going to use science to combat this movement of the Second Great Awakening. So that's what they did. And but all the theories that are in it, because they took the role of logic out, none are true. We know they're not true from logic, and so that is a problem. And as long as people like ourselves have no significant effect on the politically correct community, we're at a disadvantage. We can't improve the situation.
Yeah, I've been having a discussion with the guy about quarks, and one of the things that mainstream science say, because getting back to what this whole idea, what common sense means, it's like I would say that the whole theory of whatever, it doesn't make any sense, and the reply is that the Mother Nature does not care about whether the theory makes sense to you, and so it doesn't matter that it doesn't make any sense to me, that there's apparently all these things which don't make intuitive sense in quantum physics, for example, and they've all been theoretically been shown to be true. So therefore, this allows us to throw away our intuitive notions or our common sense notions. Although
facts that can refute it, so that's a problem. The idea of intuitive notions, I disagree with that, Franklin. I think that's not really a very good argument. Bill's Bill's point is, and I think that makes a whole lot of sense. And what I'm saying is that arguing that their argument that nature doesn't have to make sense, that's easily refutable by producing an observation that contradicts the belief. The issue with producing an observation that contradicts the belief is they reject it by saying, well, I don't agree with that because it wasn't done by, wasn't published in a journal of such and such. It's not accepted as being a valid truth by the science community, so therefore I ignore it. So that's where Bill's argument gets back to, that they've sort of abandoned the role of logic, and since now you've abandoned the role of logic, where there really aren't any observations that can refute the prevailing paradigm, because the prevailing paradigm is protected by the social belief system. So there's this bit of a problem there. I think that's what Bill is trying to point out.
Well, I think there's an intimate connection between what we consider, what we call logic, and what we consider common sense. Because I think what we're really talking about when we're talking about common sense is that we know that, for example, there's a certain set of facts which we hold as true. And what we mean by it makes sense is that we can see there's that all these assertions can be true at the same time. And when we say that something is not logical, is that we see that the set of assertions cannot be true at all at the same time. So, for example, say we're talking about quarks, and if this particle starts out with just 3 quarks, then how does it decay into basically these other different particles, all of which have 3 quarks, so that out of 3 quarks spring say 15, right? Okay, so that is kind of contradicting our notion that things just simply don't appear out of nowhere. Well, so that's something that we kind of hold true. So the thing is that
claiming physics has to go along with what you want to believe. But
no, that's not true.
You do physics too, so I don't really see this as being a very fruitful type of argument. Okay.
Well, I'm not talking about that specific argument. I'm talking about what do we mean by common sense, and what do you mean by logic? Now, you can disagree all you want about quark theory, but
common sense is what everyone can agree on because of the logical basis.
yeah, so what is the
Common
basis
sense
of
science
logical
is
basis?
science based on logic, because only logic can be agreed upon by every person. Because there are proofs in logic that you don't have in other ideas. And
Well, the thing is, I equate, abandoning logic with basically abandoning common sense. That would be my point. Well, once you are able to abandon, things that make sense, so you can accept things which have no logical explanation, then you can accept anything.
Yes, and nothing will be true.
Yes, you can accept anything. You can accept black is white. You can accept 2 + 3 = 23. You can accept anything if you're willing to do that.
There is a branch of
in your opinion, Franklin, it's your opinion that what you consider to be common sense. You take your opinion to be common sense. That's the problem.
No, that's more like, let's say, mathematics. So we feel that 2 + 3 is not 23. How do we know that? Because we knew that when we were growing up and we were learning mathematics, that numbers represent actual quantities of countable things. And if you have 2 things and then you take another 3 things and you put them together, we know that that is 5. Now, if someone says, no, that's wrong, we know that 2 + 3 is actually 23.
Well,
now that contradicts everything that you knew about numbers.
All right.
So as far as you can tell, that's wrong.
Okay, so, I want to talk about facts here. Okay, I'm going to give you, we've talked about this over and over ad infinitum, the Wakefield experiment. You know what the Wakefield experiment is, right?
No, I want to get back to something which is more easily explained, which is numbers.
Experiment is, right? You know what I'm talking about, right? You know the Wakefield experiment.
You're getting off point here. You're getting off point here, which is what is logic. The Wakefield experiment is very complicated.
We're talking about it. We have an experiment called the Wakefield experiment that demonstrates that the traditional theory of physics about electron flow is electricity is wrong. Okay? And, that has been known since the 1940s, this experiment. Okay? It's a fact.
Yes, but I did my analysis. I did my analysis of the Wakefield experiment and found it perfectly compatible with the mainstream convention, which is it is a flow of electricity.
There you go. Okay, you're not using logic.
No, I use logic.
You're not using logic. You're doing what Bill says scientists are doing, which is...
Hello? Can you hear me?
No, I use logic. Logic says that electrons, they flow through, they will create pressure waves. We know what voltage is. So if you apply all that logic, you can explain the Wakefield experiment.
No, you can't. But see, there's a disagreement there.
Well, the thing is, what the logical disagreement would be with the Wakefield experiment, which is that if you think that electricity is not a flow of electrons, then suddenly you can't explain how things like batteries work due to the chemistry.
No, you're just making up stuff now.
No, we're not making up stuff. That is all totally insane.
My point is that as long as you ignore facts of experiments that don't agree with your theory, you can continue to believe what you want to believe. And that's what Bill means by the role of logic has been dispensed with in science. That's a perfect example of it.
No, I don't think that's a perfect example. That's a very controversial example. That's why I want to get back to things like numbers. Numbers, I think, are much less controversial. No one can say that 2 + 3 = 23. But now, if you dispense the role of logic, then yes, you can say 2 + 3 is 23. Because it doesn't have to make sense to you. So it's okay that 2 + 3 = 23. In fact, 2 + 3 could equal fish. And that would be perfectly fine too. But I'm saying that contradicts all of your known presuppositions.
You're just rambling illogically, which is a large part of the problem, which is basically in science, if somebody produces a fact that you disagree with, you basically ignore it and try to argue it away just like you were doing. And that's what they're doing.
No, you do not do that. You have to go and provide an alternate explanation, which is what I do.
No, I don't.
You don't ignore it.
I don't.
You provide an alternate explanation.
I don't have to provide an alternative explanation.
I do. I have to provide an alternate explanation.
That falsifies your theory. I don't have to produce an alternative theory. I have a fact that falsifies your theory. Okay? Your theory is wrong. This experimental result falsified your theory. You don't make up a lot of ad hoc explanations. You accept that your theory is falsified. They're not doing that in science.
I don't, because that experiment does not falsify my position. Right. I mean, how is it you measure a pulse going down an RF cable and somehow that proves that electrons do not travel through the wire? I mean, that is a very complicated.
You don't understand it, so you reject it.
No, I totally understand it.
You don't have a clue what the experiment demonstrated, so you decided I'm not going to accept it because it doesn't agree with my common sense.
No, that is exactly not what I did.
You're doing exactly what all physicists do, and it's a lot easier for them to say, the smartest man in the world, Stephen Hawking, said black holes exist, and so because he's the smartest man in the world, I ought to believe what he said is true.
No, I don't do that at all. I do quite
exactly the same thing. You don't want to accept this experiment because it doesn't agree with what you want to believe.
No, this experiment totally agrees with what I want to believe. It totally agrees. It completely supports my position.
You're exhibiting what I think is illogic.
Well, one thing that we don't always do, and that is in the branch of natural philosophy that deals with logic is called meta theory, in which you have theorems that apply to all truth in every field of natural philosophy, including mathematics and other areas that we don't always include in science. You in that area, you have to, when you develop a theory, you have to enunciate what your assumptions or axioms are, and then logically derive your conclusions from that, and that's your theory. And what people don't do is they don't want to have to enunciate what their axioms or assumptions are, because they're afraid that if they do, there'll be experimental evidence that falsifies it, and that will falsify their whole theory. So they don't want to use logic. They want to do things a different way. That's what the modern scientific method does. People who lived 100 to 3,000 years ago would say, our science today, our modern science, is all bunk. It's no good. It's false. And people should pay no attention to it, because you don't take advantage of the role of logic.
Well, I mean, I think you need logic in order to prevent the rampant introduction of ad hoc hypotheses. An ad hoc meaning that you've just added in something which prevents the falsification of your theory. Now, if you ignore logic, then yeah, you can throw all those things in, and it doesn't have to be justified. That's the nature of ad hocness. And it's okay that, things are hard to explain, or you just have to postulate them, because you don't have to justify that kind of thing. Like the last time we were discussing color confinement, and I would say that which says that the only reason why we cannot observe 1/3 fractional charges is because basically we cannot observe 1/3 fractional charges.
We can.
Although there's nothing in Coulomb's law, which would say that if you have a 1/3 charge, there's no reason why it cannot exist on its own. There's nothing in Coulomb's law, and I think probably in electrodynamics, that would preclude a particle having 1/3 of a charge. There's nothing there that would do that. So that directly contradicts quark theory, which says that these things really exist. So what do you do? So you come up with an ad hoc theory that says that they are confined by this this force, and that acts like a rubber band, such that we can never separate out the fractionally charged quark. And so, voila, we don't have to explain it. Now, to me, that is like the worst kind of ad hoc hypothesis. That is the worst kind of ad hoc hypothesis. It's just sitting there just to save your theory.
Where did the idea of a quark being fractional charge come from?
From
Experiment.
Gell-Mann,
What
right?
was the experiment that made them cause them to measure a fractional charge? It was scattering of particles off of other elementary particles, and that's how they discovered that there were 3 items inside a proton, and they had 1/3 and 2/3 fractional charges. And so that's where the concept came from, not from people's ideas or imagination. In fact, they thought everything should be unit charge, like the proton and the electron have a total unit charge. But when they did scattering, they found that there were fractional charges in there, and the fractions were 1/3 and 2/3. And so they modified their theory to fit that observed data. So the question you're asking was, how could a proton, which consists of 2 or 3 quarks, how could it be decay, or a neutron, let's say, decay and produce particles, and that have some quarks in them? And the answer is, you have to have a theory of elementary particles that shows what the quarks are composed of. And, so if you want one, I published one in 2003. It was published at the International Scientific Conference in Canary Islands, owned by Spain.
Well, the real question is not that whether there's 3 things in, say, a proton. The question is why is it those things cannot be isolated? Why is it you cannot observe the 1/3 charge? And the reason given by mainstream is this color confinement argument. Do you prescribe to the same thing?
You can see, if you understand what are quarks made of. Quarks are not made of a single thing. They're complex. And in fact, if you go in the whole history of natural philosophy, you find for 3,000 years, over 3,000 years, it was assumed that all matter was made of monads, but monads had no mass, and monads could not be observed directly, but the structures made from monads could. And all matter in all forms was made by various geometrical structures of monads. So if you look at that and you ask, well, how many monads is in a quark? And if you have 3 quarks in a proton, how many total number of monads am I going to have? And then when it comes apart to different particles, can I conserve monads and explain all the different particles it can decay to? And the answer is yes. I have already done it. And the number of particles that that we have right now is over 96 particles. And so you should be able to explain all the decay of 96 particles, all the reactions of 96 particles, and all the properties of 96 particles, including predicting their rest mass. The current theory of elementary particles, the standard model, can't do that. But the monad model
do you accept
can.
the mainstream idea of color confinement, or do you reject that?
Color has no role. It's only monads. And
So
monads
you would
are
reject
toroidal rings.
the mainstream explanation that the reason why we cannot isolate a one-third charge is due to color confinement. You have an alternative to that.
So,
But you still have to explain why is it a one-third charge cannot exist, right? So what is your explanation?
well, it's not bound. You can't bind it into the a particle that can exist to an elementary particle itself. In
Okay,
other
so
words,
your explanation is that the reason why you cannot observe the one-third charge is because that particular binding cannot exist as a observable particle.
it can't observe free from the rest of the structure that it was in. So if we have three quarks in a proton or a neutron, then they can exist together in combination, but not separately, because they're not bound. And you can show that from electrodynamics. So they're not bound. So everything is based, appears to be based on electrodynamics of the monads. So that's and you see, if you have a theory that's going to compete with the standard model, which has 19 to 29 adjustable parameters representing unknown physics, not yet discovered physics, if you come along with a theory that has no adjustable parameters and no additional physics required, just let's say electrodynamics, then and you can explain more properties of the elementary particles than the theory with 19 to 29 adjustable parameters, well, that should be logically, and by the basis of simplicity, that should be the theory you should look at the most, not the theory that is more complicated. So anyway, that's the approach that I've taken, but I have assumptions, and my assumptions are all built into the empirical laws of electrodynamics. Assume that the empirical laws of electrodynamics, which we don't know of exceptions to in electrodynamics so far, otherwise we would have more empirical laws. And so these laws are my assumptions. My assumptions are based entirely on experiment. So I don't have the problem of it being falsified by experimental data, because that would falsify my starting point, which is the empirical laws. If you falsify an empirical law and come up with a new one, then I incorporate the new one in my development and come up with a slightly different. That's the basis. But when you build a theory that's not based on experimental facts, then you have a problem, because according to logic, your theory can be falsified by not being supportable by empirical data.
That was my point that I tried to make earlier about the Wakefield experiment.
Say that again?
My point to Franklin was that you got an experiment called the Wakefield experiment that falsifies the current electric theory of electricity, and so that nullifies that theory. Okay,
Well,
logic says that if you have an experimental result that contradicts the prevailing theory, you have to abandon the prevailing theory, right?
But the prevailing theory of Maxwell's equations is incomplete, because there were 6 empirical equations, and when Oliver Heaviside got the solution.
Well, we're not talking about Maxwell's equations.
I know, but I'm talking about that. You're talking about the accepted theory of electrodynamics. It's based on 4 of the 6 empirical equations of electrodynamics.
No, I'm talking about the theory that electricity flows in wires in the form of electrons.
Yes, and that is not compatible with, you have to see what's compatible with the complete set of the empirical laws. Newton said, if you only use a partial set, you will not get a true theory. You have to use the complete set of the empirical equations for a field. And if there's something that's false about it, then one of those or more of them of your empirical results are not true or incomplete. And he couldn't do electrodynamics in his day because it was very incomplete. But
well, I don't think you need the equations of electrodynamics to understand, whether what we observe with a light bulb and a battery is whether that's an actual movement of physical electrons or whether it's something else. I mean, that's what's...
Well, you don't understand what an empirical equation is. An empirical equation is thousands of experiments are explained by just that equation. Thousands of experiments. And then if you have another whole set of experiments in electrodynamics that cannot be explained by that, so you have a separate empirical law. And so you get these different empirical laws, and there's 6 of them. And so none of the empirical laws can explain any data that's explained by the other empirical laws. So you've got 6 different aspects of data that's based on experiments. And so that by combining all of them together, you have something that's compatible with all of the known experiments in electrodynamics. And so then with that, you can make more progress. And so what I've done is I found when I did that, I was able to obtain the results, not the theory, but the results that special relativity can explain in electrodynamic area. But I didn't need a special relativity nor any of its false hypotheses. I was able to explain the origin of gravity, and I was able to explain many phenomena that current theory of gravity cannot explain, including the motion of the spiral arms of spiral galaxies, for which dark matter and dark energy, which were 24 times more predominant than regular matter and energy. I was able to explain it with regular matter and energy. And also my theory of electrodynamics is based on conservation of energy, and the current theory of electrodynamics is not based on conservation of energy. It's based on the vector potential, which does not conserve energy. And so you've got all these things going on in science. And why do we have the current version of electrodynamics? Because we changed the scientific method and took the role of logic out. So since that time occurred, we have made no significant progress in modern science because all the theories we have are known to be false by logic. And Henri Poincaré in about 1908, 1910, he published the major theorems in the what's called meta theory, which is the logical rules to govern all of natural philosophy. And so he published those and he started applying them. And one of the things he applied it to was special relativity, which he had invented 1 year before Einstein and published. And he said, it's false.
Now, do you really think we haven't made any progress in how long, you say? 100 years, 60 years?
Since the time, formerly the scientific method changed about 1900.
So basically since the time of Einstein.
Just before
1902.
Einstein. Yeah. About that
so
time.
since the introduction of Einstein, you claim we've run off the rails. Although we've come up with all these things like, computers and electronics and nuclear reactors and atomic bombs and things like that, I mean, I think a lot of people would have a hard time with that claim.
Well, but you can also just take the meta theory and apply it to these theories and see why they're all false.
Yeah, but if they're all false, then how is it we are able to do all these fantastic things? I'm just saying that most people would disagree that we have made no progress in the past 100 years, I guess. So.
True progress. You can make if you have theories that are half true, something like that, you can make some progress. But for instance, let me give you an example. The biggest thing on the stock market this year has been this nanotech crystal that can produce electric power that swamps anything like solar energy and works 24 hours a day. And all the car manufacturers have each contributed $1 billion to be able to use that in their cars. The European Union has passed a law that non-electric crystal-driven cars will be illegal after the year 2040.
I haven't heard anything about that. Can you provide a reference I can look up on the internet? That sounds interesting.
Stock market. Look at the stock market. What stock has increased 45 times in value in 2 years?
Well, what stock is it?
The stock of this company in California.
Well, what is it?
Crystal. It's got some letters.
Well, what is it? What's the name?
It doesn't have it has an abbreviation, like, you know how they have abbreviations for stock?
Yes. So what is it? If it's so famous, you should know it, because I haven't heard of it.
Remember it. I'm not investing in it. I'm just telling you about it. And
I mean, but it sounds like a piezoelectric
but anyway,
crystal thing.
How did they find that now when we've had electrodynamics for 70 or 80 years? Oh no, more than that. Is 1865. We've had it for 150 years. Why, if we had a true electrodynamics, why wouldn't they have discovered that a long time ago? The answer is we didn't have a true electrodynamics. It was only partially true. So there are a lot of.
I'm interested in this. So I found there's a nanocrystal. Is that what we're talking about? Nanocrystal electricity stock.
Yeah, it's a stock in a company that makes this crystal. And they'll be in everything. They'll be in your cell phone. They'll be in every electrical appliance in your house. They'll be in your car. They'll be, you won't have electrical outlets anymore because you won't need them. Everything will have its own source of power. That's why everybody is jumping on the bandwagon, because if you don't, who will want to buy your stuff? I mean, think about it. You don't have a battery in anything. You don't have electric power plants. You don't have wires distributing power. All that stuff is going away.
Well, this is probably the biggest thing I've never heard of. But I'm looking at this article saying that, oh yeah, they're claiming all these things that you're saying here. But
I saw Stephen Hawking's name in there too.
Yes, they threw Stephen Hawking's name in there. He thought it was the most amazing. But this looks like a fraud to me.
That makes me get a little skeptical.
I mean, this sort of thing looks like a gigantic fraud, typically, where they're announcing this stuff.
Before they sold their stock, they had public meetings for the big investors, including companies like Amazon. Amazon put $1 billion into this company. The major car manufacturers, after they saw a car running on it and they got to look at it and everything, they put $1 billion too. And so they're not. It's not that they don't see it work. They see it, and they see it, examples of it, and they know that it's going to have a tremendous impact.
Well, so far, scrolling through this gigantic advertisement here, I don't find any actual stock being mentioned here. So I remain skeptical. Typically, when you see something like this, they're trying to fraudulently tell you to go buy their stock picking thing. Now, see, if this was true, then I would have seen an actual stock mentioned here.
You just, it's infuriating. You just, I don't believe that. I don't believe it. I don't believe it. Okay, let's just, drop this.
I'm looking for the actual stock here.
There was an announcement this week where these astronomers discovered that all galaxies rotate at the same rate. You understand what that means? They discovered that galaxies, all the disk galaxies that they looked at, all of them rotate at the same rate. That says there's a universal clock, because all the galaxies that they looked at, they're all rotating at the same rate. Okay? This has actually been announced. All right. Question: will this discovery turn out to be accepted by the mainstream community? Take a look and see what happens to this.
Happens to what? Happens to that?
I just told you about a major discovery that's been announced that contradicts every belief that mainstream has adhered to for however long you want. That there must be absolute time because all galaxies rotate at the same rate. Okay? What's going to happen to this announcement? Is that going to be accepted or not? What do you think?
Well, obviously you heard about it, so it was actually, it's been publicized.
Well, I'm saying look to see what happens and how they interpret this. How are they going to interpret this? They say there's no such thing as absolute time. If there's no absolute time, how is it that all galaxies rotate at the same rate?
Let's look up this discovery here. Galaxies rotate at the same rate. Now, by that, you mean they take the same amount of time to complete a rotation, so the Andromeda and Milky Way rotate at exactly the same rate?
Know. Look it up. And I hate that you do this. I hate that you do this. I hate this, hate this, hate this.
I'm just asking questions. Now we've got this thing here, galaxies, and I'm just trying to understand what you're saying.
You're wasting my time with this, okay?
I'm just asking questions about something that you brought up, so I don't know how that's wasting your time.
You're wasting my time while you're putting this on the internet. Everybody out there can look this up, okay? You just had it on there. But anyway.
Galaxies, large and small, rotate at similar rates.
Well, they're using the word similar. I say I don't know what they mean by that. Okay.
Well, that's why it's important to see.
Point is, what are they going to do with this idea that contradicts? I mean, it seems to contradict everything that you think is true, right? About what they've been saying. There's no absolute time. If there's no absolute time, how are these galaxies rotating at the same rate?
So they say appear to rotate at approximately once every billion years. So they're saying every galaxy, no matter big or small, rotates. But if they say not every galaxy rotates precisely once every billion years. So that would kind of, so it's not precisely. So it's an approximation.
So what you're doing now, see, now you're doing what the mainstream do. You say, oh, well, we got to question this fact now.
Well, yes, we always have to question facts. Everyone does that.
Question this fact. We can't accept it. It doesn't fit into our thinking pattern. We got to reject this fact. What if it's a true fact? Why are you rejecting it?
I'm not rejecting it. We're just reporting on what is.
Yeah, you are.
What is the? No, I'm not saying. I'm not saying that they don't rotate precisely once every billion years. Apparently, this is what they're reporting. That given the range of reported.
So my point is, given that this seems impossible and highly improbable, what are they going to do with this?
Someone will try to explain it. Probably this will cause people in the, say, the dark matter camp or the modified gravity camp to try to fit this into their theories.
Why would you want to try to fit it into your theory?
I mean, currently mainstream doesn't really even have any explanation for basically the flat rotational curves. I mean, this is why we have the ad hoc invention of dark matter. This is an area that mainstream will clearly tell you, no, we don't know what's going on here. So there's not like they have a dog in this fight.
Well, it seems rather bizarre to me that they could even approximately rotate at the same rate, or even, I mean, how would that even be possible? I mean, how can one galaxy know what its rate of rotation is? How can they be coordinated at least closely enough that they can make a measurement that say that they even seem to appear to be reasonably close in their rotation rate? I mean, that just seems bizarre. Okay.
Well,
I mean,
Theory.
science.
What
Theory, you can
diameter
come
do
up
they
with
rotate
theory.
at the same rate
huh?
at?
Excuse me?
At what diameter do they rotate at the same rate at? Because the rate of rotation is different based on the diameter.
Well, that's what they're
Well,
saying.
you'll
It
have
doesn't
to
matter.
read the paper. You'll have to read the paper.
That's what they're saying. It
I mean,
doesn't matter. Big galaxy, little galaxy, they will rotate approximately once every billion years.
Right.
But within each galaxy, depending on the diameter, the rotation period is different.
Yes,
I
but I
mean,
think they're
even
talking
within the
about
galaxy, even within the galaxy itself, the rotation rate of any particular section of the galaxy is dependent on the radius from the center of the galaxy.
well, that's probably true, but you have to go find
Now, the
out
rate of
what they're doing there.
by rate of rotation, they mean that the thing does one revolution, one rotation, like the Earth rotates once every day. It doesn't matter whether you're on a mountaintop or in Death Valley, you still rotate once a day.
Well, I think he's saying
but
that
the
like the
galaxies
inside
aren't
of the
solid.
galaxy will rotate faster than the outside. I mean, the inside of the galaxy could rotate twice, just like the planets, inner planets, will rotate 2 or 3 times before like Pluto goes around once.
I'm not saying it's true or not true. Okay. I don't know. I'm just saying, look at this and pay attention to how this is dealt with by the scientific establishment. Okay. It's not about whether you want to believe it or not believe it. You can believe whatever you want. What is the scientific establishment? What are they going to do with this? How are they going to react to such a thing that seems so completely alien to their belief system?
Well, I think the article is stating this right here. It says the findings proposed by the study are revolutionary. They could potentially validate existing or upcoming theories concerning galaxies and the stellar formation that takes place.
Thank you for that, Franklin. I can read and I can think. I figured that out for myself as soon as I heard about it. I didn't need to have to read it.
But is that not the answer you were looking for?
That's not an answer. That's not what I'm saying. What are they going to do with this fact, this observational fact that's out there? Are they going to deny that it's true? Or are they going to accept it it's true and then try to fit it into their theories? What are they going to do with this fact? This is an observational fact. How do you deal with an observational fact that seems so extraordinarily contradictory to everything that makes common sense? This seems to me to be completely in violation of common sense.
But the statement that they could potentially validate existing or upcoming theories is actually interesting and might suggest that they will consider twisting this around a bit so that they actually validate some current theories rather than contradict them. I assume you can hear me, by the way. I couldn't get my microphone to work before.
Yeah, we can hear you.
That was my point, Ian, which is it would be interesting to see what approach they take. That was my point. Okay.
Okay.
How are they going to handle this? What are they going to do with it? Are they going to decide that it's not a true fact? Are they going to try to incorporate it into their theories? How are they going to incorporate it into their theories? Are they going to take it as something that, because if you accept that it's reasonably true that all the galaxies are rotating, every galaxy rotates 360 degrees in the same time. Okay, that sort of says to me, my first reaction was, that's really pretty extraordinary. That sort of implies there's a universal absolute time.
Well, one thing they haven't taken into consideration in the past, and it's unlikely that they will do so now, is that when we look at a galaxy, we're not actually looking at a snapshot. We're looking at really a composite picture of all the elements of the galaxy that are distant from us, such that the light has actually reached us at a particular time. So it's a relationship between the actual parts of the galaxy that are distant from us, equal to the light years distance that they are from us, because otherwise the light will have passed us or it will not yet have reached us. So it's really a composite image, and it's really more complicated than they imagine. So I don't suspect they'll consider that, because they haven't heretofore.
All right. Well, it looks like we are getting towards the end of our time here. So I'll go ahead and make a summary. So today's discussion was started off with a discussion of Stephen Hawking and whether he was indeed the smartest man in the world. So in our looking around the internet, seems like he is famous for mostly Hawking radiation and all the books he published, and generally just as an ambassador to the public for science. So, and he won several awards, and he had like the same position as Newton. So, but some of the other websites that we went to, with like asking whether he was the smartest man in the world, pointed out that, he probably wouldn't make it on the list of top 20 physicists, and that his contributions haven't been, that significant, perhaps. But certainly he was famous. So, and the question was asked, do we believe in this Hawking radiation because it really exists and that we have experimental evidence for it? Or was it just something that happens out of popularity, and that we just like Stephen Hawking and what he's saying sounds cool, so we can just agree to believe in that? And this brought up the question of, the role of logic being ignored. So are we ignoring the role of logic in things like Hawking radiation, and particularly, what is logic, and is that the same thing as what we would call common sense? And does that prevent us from doing things like accepting ad hoc theories? And I brought up say quark theory, and Bill brought up this apparently nanocrystal development, which is apparently the biggest thing I've never heard of. That why wasn't this invented previously? And that may be due to a misunderstanding, lack of understanding for how electrodynamics works. And then Harry finally brought up this other new fact we haven't heard about, which is that all galaxies rotate at approximately once in a billion years. So Harry wants to know, what are they going to do with this result? Are they going to say it's false? Are they going to ignore it? Or are they going to accommodate it? My guess is they're going to try to accommodate it. They're probably going to add some ad hoc thing into their theories. I think this would be more of a problem for dark matter theorists, who would probably have to explain why is it that the rotational rate is about the same. So those are all very interesting topics. So I thank everyone for participating today in our science chat, and we will see you again probably next week. All right. So thank you.
Thank you.